Welcome to NPTEL video series of CAD lectures. This is lecture 9, Transformation of Solids. The question that we ask, why transformations? Geometric transformations provide soul or life to virtual objects. Operations like rotation, translation, reflection, and scaling are used a great deal during geometric modeling. You might want to think about set operations. Say I have two solids in my hand, solid 1 and solid 2. I need to maneuver or manipulate the position and orientation of solid 2 with respect to solid 1 to be able to perform set operations. Unless I do that, I will not be able to perform set operations. There has to be a part of solid 1 intersecting with a part of solid 2 to perform addition, subtraction, intersection, and union like operations. The second example, feature design. Let me first draw a general curve here. And then finally change the positions of all these points. What this does is it allows me to change the local shapes of these curves. Many curves constitute surface patches, so moving these points or transforming these points allows me to change the local shape of those surface patches as well. I can go ahead and locally change the slope at a point. I will not be able to do feature design unless I perform transformations. Object transformations are also used in applications like animation, robotics, and virtual reality. A set of points compose a curve. We are going to be discussing curves later in the course. A set of curves make a surface, and a set of surface patches represent a solid. We have learned this before. This is the extended Jordan curve theorem. In a sense, what we are doing is to be able to change the shape of a solid locally, or the shape of a surface patch locally, or a curve locally. All we need to do is reposition the points appropriately. In other words, all we need to do is to perform transformations on points, and the local shapes of surface patches and solids will change automatically. To reemphasize, it is always the transformations of points we are interested in. Transformations are essentially functions. Just in case if you have forgotten what functions are, here is a quick recap. A function f is a map from u to v. U is called the domain, and v is called the range. U and v are two sets. V is also called the image of u, and u is also called the pre-image of v. In our case, we are performing transformations in the Euclidean space E3, and so u and v are E3. Let's look at the definition of a function. Say we have a few elements in the domain U, and correspondingly we have a few elements in the domain V. Some elements in U are related to the corresponding images in V. Note that one element in U is not related. This is not allowed in a function definition. Elements in V can exist without any relation. This is allowed, but elements in U existing without any relation or without any image is not allowed. In other words, this is not a function. Transformations, the definition. A transformation is a one-to-one and an onto map. Let's see what different map types are. In this figure, this is the domain U and this is the range V. All the elements of U have corresponding images in V. The images are also unique. But notice this element in V. It does not have any preimage. This is a one-to-one map and not an onto map. Let's try to see what an onto map is. We have a few elements in the domain set, and then we have a few elements in the range set. Notice here that these two elements have a common image, and further, there are no elements in the range which are vacant. Such a function is an onto function and not a one-to-one function, because two elements in the domain have one image over here, for which reason it is not a one-to-one function. Look at this function here. All the elements in the domain set have respectively unique images in the range set. There is no element in the range set which is vacant. This is a one-to-one and an onto map, which is what transformations are. Let's say we have a point P and T of P represents the transformation of that point. If T of P1, which is the transformed position of P1, and T of P2, which is the transformed position of P2, represent the final locations of points P1 and P2, then if T of P1 equals T of P2, then P1 equals P2, and the converse is also true, that if P1 equals P2, then their respective images are the same. In other words, for every final location T of P, there must exist its preimage P. Physically, this is what it means. Look at this solid here. It has 8 vertices. If I move this solid from this position to this position, I should be able to move it back to the previous position. This should be allowed by any valid transformation. If it is not allowed, then we are in trouble. In other words, reversing a transformation must be allowed. Rigid body transformations. Let's take a look at rotation in 2 dimensions. We have an xy plane and we have a point P sub j with coordinates xj and yj. Let me rotate this point about the origin O to a new location Pj star with coordinates xj star and yj star. Let me also draw 2 position vectors joining the 2 points to the origin. The length of the position vector joining Pj and 0 is L. Since we perform rotation, the length of the vector that joins the origin to Pj star doesn't change. Let alpha be the angle between the position vector 0 Pj and the x-axis, and let theta be the angle by which point Pj is rotated to Pj star. We can determine what the abscissa and ordinates of Pj and Pj star are. This is xj star, which is projection of this position vector on the x-axis. This is xj, which is the projection of pj on the x-axis. This distance is yj, which is the projection of pj on the y-axis. And this distance here is yj star, which is the projection of pj star on the y-axis. We can write the relation between xj star, theta, xj, and yj using trigonometry. Clearly, xj star is L times cosine of theta plus alpha. Expanding this gives L times cosine of alpha times cosine of theta minus L times sine of alpha times sine of theta. Notice that L times cosine of alpha is xj, and L times sine of alpha is yj. Likewise, yj star is L times sine of theta plus alpha. Expanding which gives L times cosine of alpha times sine of theta plus L times sine of alpha times cosine of theta. Once again, L cosine alpha is xj and L sine alpha is yj. I can write these two relations in compact form using matrices. Here we have a column vector that include xj star and yj star. Here we have a 2 by 2 matrix, cosine of theta minus sine of theta, sine of theta, cosine of theta, and this is a column vector including xj and yj. If I multiply this matrix with this vector, xj times cosine theta minus yj times sine theta is xj star, and xj times sine theta plus yj times cosine theta is yj star. If I treat the column vector as an ordered pair of coordinates using short form, I can write that position vector pj star equals R, the matrix R that pre-multiplies the position vector pj, where R is cosine of theta minus sine of theta, sine of theta, cosine of theta. We call R as a rotation matrix. Let's consider an example of rotation in 2 dimensions. A lamina ABCD in the xy plane with coordinates of A as 6, 1, coordinates of B as 5, 5, C as 2, 3, and D as 4, 4 is rotated about the z-axis, which is coming to you, by 45 degrees. A star, B star, C star, and D star are the new positions of these vertices. A, B, C, D are the old positions. Notice how I'm writing this matrix, which is a 4 by 2 matrix, and the transpose of it. In a sense, what I'm doing is, through a single matrix multiplication operation, I'm rotating all the 4 points. Of course, I pre-multiply this matrix by the rotation matrix. Cosine of 45 degrees minus sine of 45 degrees, sine of 45 degrees, and cosine of 45 degrees. It is not difficult for us to work out the math, but it's more important to understand how the final position of the lamina looks. In this figure, the lamina in blue is in its original position. Lamina in red is in its final position. Origin is somewhere here. Translation 2 dimensions. We have the two-dimensional xy plane. We have a point pj, coordinates xj and yj. Let's translate this point through this vector to its final location pj star with coordinates xj star and yj star. The translation vector has components p and q. In other words, p is the amount of translation along the horizontal direction and q is the amount of translation in the vertical direction. xj star equals xj plus p, yj star equals yj plus q. Once again, I can write these two equations in compact matrix form. Column vector xj star yj star equals column vector xj yj plus column vector p q. Note that in rotation we were using a matrix to pre-multiply a column vector, but here we are using the addition operation. There is a slight discrepancy, but we'll address that later. In short form, position vector pj star equals position vector pj plus a free vector p. Translation and example. The lamina ABCD with the coordinates of A as 6, 1, B as 5, 5, C as 2, 3, and D as 4, 4 is to be translated through a vector V with components 2 and -1. Once again, we perform all translation operations simultaneously. A star, B star, C star, and D star are the new positions of ABCD. Here, all the coordinates of ABCD respectively are mentioned, and they are all translated by 2, -1. These are the new positions of the 4 points: 8, 0, 7, 4, 4, 2, and 6, 3 respectively for A star, B star, C star, and D star. In the figure, the lamina in red is in its initial position, and the lamina in blue is in its final position. To eliminate that discrepancy that I talked to you about earlier, translation may also be expressed as a matrix multiplication operation, just like rotation. You would notice later that it will make our lives a lot easier. For that, what I need to do is, in the column vector, I need to introduce an additional entry, 1. Here again, I introduce an additional entry 1. You can clearly verify by pre-multiplying this matrix with the old column vector. The translation matrix is 1, 0, P, 0, 1, Q, 0, 0, 1. 1 times xj plus p times 1 is xj plus p, which is xj star. 1 times yj plus q times 1 is yj plus q, which is yj star, and 1 times 1 equals 1. Note that without the introduction of the additional entry in the position vectors of both the new and the old points, it would have been difficult for us to express translation as a matrix multiplication operation. In short form, pj star is T, the translation matrix, times pj. Once again, the translation matrix T is given by 1, 0, P, the first row, 0, 1, Q, second row, and 0, 0, 1, the third row. Combined rotation and translation. But a little bit about the additional entry that I had introduced in the position vectors earlier. So this column vector with entries xj, yj, and 1 are now termed as the homogeneous coordinates of Pj. Xj, yj would have been the natural coordinates. You would see these coordinates coming in a lot of use in areas like robotics and vision. First, rotation in homogeneous coordinates. Remember that we still have rotation in the natural coordinates. We would need to modify the rotation matrix appropriately from its 2 by 2 size to its 3 by 3 size. That is not very difficult. So the column vector on the left is xj star, yj star 1, cosine of theta minus sine theta, cosine theta was the original 2 by 2 rotation matrix. Now we have a third row and a third column. All the entries in the third row except for the last one are 0, and all the entries in the third column, again except for the last one, are 0. The 3 by 3 entry in this newly constructed rotation matrix is 1. Xj, yj, 1 are the homogeneous coordinates of Pj, mentioned earlier. R is now my new rotation matrix with elements cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. It's a 3 by 3 in size. Let's now perform translation after rotation. So we have the original point P. It is rotated to a point P1. We know the algebra. x1, y1, 1 would be the homogeneous coordinates of P1 equals a rotation matrix pre-multiplying the column vector x, y, 1, which are the homogeneous coordinates of P, and then P1 is translated to a new position, P2. The translation vector has components P and Q, so we can substitute this expression to replace this column vector. Once we do that, we have the translation matrix pre-multiplying the rotation matrix, which in turn is pre-multiplying the original column vector. This is the short form. We can multiply this 3 by 3 matrix, which is the translation matrix, and this 3 by 3 matrix, which is the rotation matrix, to get cosine of theta minus sine of theta P, sine of theta, cosine of theta Q for the second row, and 0, 0, 1 for the third row. Instead, had I performed rotation after translation, things would have been slightly different. In this case, the final position of the point gets determined by the original position of the point, which is pre-multiplied by the translation matrix, and this is pre-multiplied by the rotation matrix. This 3 by 3 system here, we all know, is the rotation matrix, and this 3 by 3 system here is the translation matrix. If we work out the algebra, we get cosine of theta minus sine of theta, P times cosine of theta minus Q times sine of theta in the first row, sine theta, cosine theta, 3 times sine theta plus q times cosine theta in the second row and 0, 0, 1 in the third row. Appreciate the difference between this 3 by 3 transformation matrix and this 3 by 3 transformation matrix. They are not the same. Or in other words, for specific values of p and q and theta, they would be the same. Not always. And this is what we know from matrix algebra. Two matrices, A and B, if multiplied together, that is A times B, would not give the same result as B times A if multiplication between A and B is permitted. Bottom line, the two transformations are not equal. Let's take an example of combined rotation translation. Lamina ABCD with coordinates of A as 3, 2, B as 5, 5, C as 4, 1, D as 4, 2.5 respectively is first rotated through 60 degrees and then translated by a vector 2 minus 4. We can do the math. We know the results from the previous slide. This is the case of rotation and then translation. Once again, I'm performing transformation on all the 4 points simultaneously here. This is the result I see. The lamina in blue is in its original position. This is rotated about the origin by an angle 60 degrees to the green position here, and then translated by the vector 2 minus 4 to the red position here. Note the position, or note the average position of this red lamina, somewhere around the x coordinate of 2 and y coordinate of 1. Had we performed this transformation the other way around, that is, first we would have performed translation and then rotation. Translation by vector 2 minus 4 and rotation by an angle 60 degrees. We would have gotten slightly different results. Once again, we know this result from previous slide. All we need to do is substitute for values, for variables appropriately. If we plot the 4 points in different positions, we see this. The lamina in blue is the original position, first translated to the green position and then rotated to the red position. Note two things here. The orientation of the final position of the lamina here and here are the same, but the positions are slightly different. This is located somewhere around the x coordinate 5 and y coordinate 8, where this lamina is located somewhere around the x coordinate of 2 and y coordinate of 1. Bottom line, the order of transformations is very important. We cannot change the order in transformations and expect the same result. Next, rotation about a point. So far we have covered rotation of a point about the origin, but this case is slightly different. We would like to rotate point Q about point P. This is again in 2 dimensions. What do? We can use the knowledge that we have gathered before on both translations and rotations. Rotation of Q about P, of which the position vector or the components of the position vector are P and Q, small case, can be performed in the following steps. One can think of translating first point P to coincide with the origin, like here. Point P can be translated to coincide with the origin. The new position of P is P prime. The orientation of this line segment doesn't change. Step 2. One can then perform rotation about the z-axis, which again is coming to you by an angle theta, like so. This line segment is rotated by an angle theta about the origin. And finally, one can place the point P back to its original position, like so. The three concatenated translation, rotation, and translation operation, or inverse translation operation in this case, is equivalent to point Q getting rotated by an angle theta to a new point Q star about the point P. We can work out the math. If we think about arranging different transformation matrices, again, let me remind you that we are working with homogeneous coordinates here. Xq star, Yq star, and 1 are the homogenized coordinates of the new location of Q star. And Xq, Yq, 1 are the homogeneous coordinates of the previous location of Q. Of course, there are three matrices corresponding to three different transformations. The first one was translation of P to 0. Notice the appearance of minus signs over here. The next was rotation of Q about the origin, which is given by this 3 by 3 rotation matrix. And the third operation was inverse translation that allowed P to move back to its original position. A remark here. Notice how all these transformation operations are getting concatenated as matrix multiplication operations. This is what the homogeneous coordinates allow us to do, to combine translation and rotation transformations as matrix multiplication operations. Next, reflection. Let's see what happens when we reflect a point about the x-axis. Well, when we reflect about the x-axis, then the abscissor remains the same, the ordinate changes in sign, and 1 remains 1, the third dummy entry for now. We can express these relations in the matrix form. So we'll have a 3 by 3 matrix here. The first row is 1, 0, 0. The second row is 0, minus 1, 0. And the third row is 0, 0, 1. In short, this 3 by 3 matrix is represented by R sub fx, pre-multiplying the original column vector of the point. Likewise, reflection about the y-axis. In this case, the abscissor changes in sign, the ordinate remains the same, and the dummy entry again remains the same. We can express this using again a 3 by 3 matrix with entries minus 1, 0, 0, 0, 1, 0, and 0, 0, 1. This 3 by 3 matrix is represented as R sub Fy. These are the two reflection transformation matrices about the x and y axes respectively. Let's consider an example on reflection. A lamina ABCD with coordinates of A as 3, 2, 1. Here we are using the homogenized coordinates. Coordinates of B as 5, 5, 1, C as 4, 1, 1, and D as 4, 2.5, 1 is to be reflected through the y-axis and then the x-axis. These are two separate reflection operations. I perform the reflection operations simultaneously on all the 4 points of the lamina. This is as if I'm stacking the homogenized coordinates of A, B, C, D column-wise and constructing a matrix and then pre-multiplying this matrix by a reflection matrix. Reflection about the y-axis. Working out the math is not difficult, but graphically, this is what the situation is. The lamina in blue is in its original position, and the lamina in red is the reflected position. This is the vertical axis. If I perform a reflection about the x-axis, then this is how the figure looks. The lamina in blue is the original position, and the lamina in red is the final position. This is the axis of reflection. Now let's consider a generic transformation of reflection about an arbitrary line. Let's say we have a two-dimensional patch S here, which is to be reflected about the line LD. How do we go about constructing various intermediate transformation operations? Let's see. A remark here, note that these intermediate operations will not be unique. You can choose to work with different operations if you like. Step 1. Translate point D with homogenized position vector PQ1 to coincide with the origin, shifting this line L to a new position L star. Line L has gotten translated so that point D coincides with the origin. Along with that, S has also gotten translated. Step 2. Rotate L star to L double star by an angle theta such that this line coincides with the y-axis. This is the operation. This line is rotated by an angle theta to coincide with the y-axis. Notice that the patch S has also been rotated accordingly. Step 3. Reflect S about the y-axis. Graphically, this picture depicts the reflection. Next step, rotate L double star through minus theta to bring it back to L star. In other words, I need to rotate this line to bring it back to this position. Like so. and then finally translate the line L star to coincide with its original position. This is the pictorial representation. Line getting translated to its original position. Here. Compare this figure with this figure and observe how the solid has been reflected from here to here. Transformation algebra. Notice that we are performing 5 transformation steps. 1. Translation. 2. Rotation. 3. Reflection. 4. Inverse rotation. And 5. Inverse translation. In numbers, these transformations appear like so. The first is the translation matrix. The second is the rotation matrix. The third is the reflection matrix about the y-axis. The fourth is the inverse rotation matrix. Note here that I have used minus theta instead of theta. So there is a corresponding change in sign, in the sign terms. And the fifth matrix is the inverse translation matrix. Notice how the transformations have been concatenated. We are concatenating transformations from right to left. In short, the transformations are written from right to left as T, the translation matrix, R of theta, the rotation matrix, R of Fy, the reflection matrix, R of minus theta, the inverse rotation matrix, and T, the inverse translation matrix. One can as well think of reflecting a geometric entity through the origin. Both the abscissa and ordinates would change sign in this case. This transformation can be represented in the 3 by 3 matrix form as -1, 0, 0, 0, -1, 0, 0, 0, 1. In short, we call it reflection about the origin, R sub FO, operating on the original homogenized position vector of a point. One comment, an important comment here, is realize that we are performing transformations only on points. An example of reflection through the origin: a line with endpoints P and Q with coordinates 2, 4 and 6, 2 respectively, when getting reflected through the origin, the math of that can be worked out, no problem. Looks like this. This is the original line, PQ, and this is the final line, P star. Rigid body transformations have a peculiar property. Let me explain this to you on the board. Let T be any generic transformation with components A, B, C, D, E, F, G, H, I. You can think of T as a combination of various operations the transformation operations we have studied so far. Let me draw 2 lines of a polygon. This polygon can be of any shape. I'm only interested in two contiguous lines of this polygon. Let me represent these two lines in vector form. Let's say this is V1. Let's say this is V2. And the included angle is theta. If this polygon undergoes transformation T, the orientation and position of this polygon will change. Let's say the new orientation is like so. This is V1 prime, this is V2 prime, and the rest of the polygon. The included angle, let's say, is alpha. If T is a rigid body transformation, what do we expect? Well, we expect that the magnitude of V1 prime is the same as magnitude of V1. The magnitude of V2 prime is the same as the magnitude of V2, and the included angle theta is the same as alpha. If these three conditions for the two vectors and the included angles are not satisfied, then this would not be a rigid body transformation. I can rephrase these conditions slightly differently. I can say that V1 dotted with V2 is the same as V1 prime dotted with V2 prime, and V1 crossed with V2 is the same as V1 prime crossed with V2 prime. A little note about these vectors V1, V2, V1 prime, and V2 prime. Let me represent this vector here by 2 points A, B, and let's say the coordinates of A, the homogenized coordinates of A are A1, A2, 1, and those of B are B1, B2, 1. Notice that with respect to some origin, A and B will be position vectors. By vector algebra, V1 equals B minus A, and in component form, this is B1 minus A1, B2 minus A2, and 0. Notice this entry here. For free vectors, this entry will be 0. Once again, for free vectors like V1, V2, V1 prime, and V2 prime, the third entry will be 0. But for position vectors, the third entry will be 1. With that said, let V1 be equal to V1x, V1y, 0, V2 be equal to V2x, V2y, 0, V1 prime equals V1 x prime, v1 y prime 0, and note that this is nothing but the transformation a, b, c, d, e, f, g, h, I operating on v1 x, v1 y, and 0. Likewise, v2 prime equals v2 x prime, v2 y prime, and 0, and this is nothing but the transformation a, b, c, d, e, f, g, h, I operating on v2. Using this relation, one can get the components v1 x prime, v1 y prime, or v1 prime in terms of v1 x and v1 y. And using this transformation, one can get the components of v2 prime, which are v2 x prime, v2 y prime, in terms of v2 x and v2 y. I'll leave the algebra for you to work on. Once we get these components, we can plug them back into these conditions here. And compare different terms like v1x, v1y, v1x, v2x, v1x, v2y, v1y, v2x, and so on and so forth. You will quickly realize that for these transformations to be valid for any v1, v2, v1 prime, and v2 prime, you will have to have the values of g as 0 and the value of h as 0. Here again, g would be 0 and h would be 0. Let's skip the algebra and see what we have. If we use this condition, v1 dotted with v2 equals v1 prime dotted with v2 prime, and if we compare the terms v1x, v2x, we get a squared plus d squared equals 1. If we compare v1y, v2y terms, we get b squared plus e squared equals 1. If we compare v1x, v2y, or v2x, v1y terms, then we get ab plus de equals 0 in both cases. If we use the cross product condition, v1 crossed with v2 equals v1 prime crossed with v2 prime. If we compare the v1x, v2x terms, we get ad minus ad as 0. For the terms v1x, v2y, we get ae minus BD equals 1. We get the same relation if we compare V1y V2x terms, and for V1y V2y we get BE minus BE equals 0. So these are 4 important relations that relate different entries in the transformation matrix. Note that these are 4 equations in 4 unknowns: A, B, D, and E. Nowhere would C, F, and I come in picture as of now. Let's concentrate on these 4 variables which form the top left 2 by 2 matrix, and let's perform this operation: AB DE transpose AB DE. If I call this matrix M, then this is M transpose M. On working the algebra out, this would give me A squared plus D squared, AB plus DE, AB plus DE, and B squared plus D squared. Look at these relations here. It will be not difficult for you to figure that this is nothing but a 2 by 2 identity matrix. And this is precisely one of the properties of transformation. This 2 by 2 submatrix is orthonormal. Orthonormal matrices are those for which M transpose M, if M is to be an orthonormal matrix, then M transpose M equals I. How about this 4th condition here? AE minus BD equals 1. Look at the determinant of this 2 by 2 submatrix. AE minus BD equals 1. Physically, it is these 4 conditions that do not allow the magnitudes of different interplacements between points and the included angles to change after transformation.